Let's prove another wonderful theorem of Cauchy, this being Cauchy's integral theorem. Suppose we have some open subset of the complex plane U, which f is analytic on, which just means we can differentiate it within this subset. Furthermore, we have some path of integration gamma inside of U. Well, Cauchy's integral theorem tells us that if we integrate f over this path gamma, what we'll get is 0 every time. And you'll notice that I didn't specify anything about gamma except that it's a closed loop. So this is much like the fundamental theorem of conservative vector fields. Let's try to prove this statement. Let's recall that when we have some complex function f of z, we can split it into two functions, a u of xy plus I times v of xy. Now you may recall that if your complex function f is analytic, that means that the component functions u and v will satisfy these equations, called the Cauchy-Riemann equations. And that's that the partial of u with respect to x is equal to the partial of v with respect to y, and the partial of u with respect to y is equal to the negative partial of v with respect to x. So to start our proof, we're going to start with this integral of f along the path gamma, and now we're going to break things into u and v for both f of z and dz. We already went over how we can rewrite f of z, but then dz is easy to rewrite because z is equal to x plus iy, so dz is dx plus I dy. So we'll substitute u plus iv for f of z, and we'll substitute dx plus I dy for dz, and then we're going to multiply everything out to get here. And then next, I'll just group our integrals into terms of real parts and imaginary parts to keep things clean. And now that we're here, our next step will be to invoke Green's wonderful theorem. Green's theorem tells us, if you don't remember, that if we're integrating some sort of vector field along a closed curve, then that's the same as if we integrated the curl of that vector field all throughout the area bounded by that curve. And both this real and imaginary integral are in the form of this vector field along a closed curve. Let's just quickly call the area bounded by gamma w, and then rewrite these integrals in terms of curls over w. So let's apply Green's to this real integral here. What we'll get is the negative partial of v with respect to x minus the partial of u with respect to y, and by Cauchy-Riemann, we know that negative dv dx is equal to du dy, so this first integral goes to 0. Similarly, with the imaginary integral, we'll get partial u with respect to x minus partial v with respect to y, but we know that partial v with respect to y is just partial u with respect to x, so this integral will also cancel out and go to 0, meaning that our original integral over the curve gamma goes to 0. And with that, we're done. We've proved the statement. So if you have some function f of z that's analytic over some subset of the complex plane u, and you integrate it along a closed path anywhere within that subset u, you're going to get 0. And that's an amazing fact about analytic functions. Thank you for watching, and have a nice day. More complex analysis later.